My name is Karen Daly and I teach mathematics at DKIT, a third level college in Ireland. This video was produced to further assist my first year computing students with their mathematical studies. At the end of this tutorial, you should have gained an understanding of the fundamentals of transformations, which includes how to apply translations, rotations, scaling and reflection to a point or a series of points. Enjoy! Let's begin by looking at 2D transformations. So what is 2D first? Well, 2D means two dimensions, and you're used to representing two dimensions graphically on the Cartesian plane. The Cartesian plane looks like this, where you have an x-axis and you have a y-axis. And you can represent any point on this axis by putting it in using a scale. So let's say I had a 1 there and I had a 2 there, and this point here would then be 1, 2. So 1, 2 is a two-dimensional point. Let me just write that down here. It's a two-dimensional point. Okay. And that's my 2D. Now, what about the word transformation? A transformation is a word that describes the movement of a point around the Cartesian plane. For example, if we look at the point drawn, the movement could be upwards. I could move the point up the y-axis. It can be downward, down the y-axis. It could be to the right, which would be along the x-axis, or it could be to the left. A collection of 2D points will form for you an object on the Cartesian plane. So let me give you an example of that. Here's the Cartesian plane. Let me do it here. Let's say you wanted to form a triangle, right? Well, to form a triangle, all you would need is 3 points on the Cartesian plane, and then if you join these 3 points, you would get a triangle. You can apply transformations to objects such as this triangle. One such transformation might be to magnify the triangle by a given factor. So let's say I magnified it by a factor of 2, let's say, or 1.5, that looks like. My triangle would then get to look like this. It would have grown by a factor of 1.5. Likewise, you could shrink the triangle to make it smaller. You could even rotate the triangle about either the origin, or you could rotate the triangle about an arbitrary point. So these are all examples of transformations. So let me recap. A transformation is a word that describes the movement of a point or an object around the Cartesian plane. In this tutorial, I'm going to look at 4 different types of transformations. First one is translation. The second one is scaling. The third one is rotation. And the fourth one is reflection. Now I'm going to look at these singly and in combination. I'm going to represent each of these transformations by their own individual matrix, and I'm going to implement then the transformation by matrix multiplication. So if you need to revise that, you can look at a previous tutorial that I have made on matrix multiplication. So let's look at these transformation matrices. The first one I'm going to look at is translation. So in the exam, you'll be given just this part of the formula. You'll be given the actual matrix and you'll be told that this is a translation matrix. The understanding of it you need to have yourself. The understanding is written here. It says, suppose that a 2D point is translated. Translated is just a fancy word for moved. So it's moved by an amount A in the x direction, and A is just a value. So let's say it was moved by 4 in the x direction and a value b in the y direction. So let's say it was moved by a value b, I'll write it here, b is equal to, let's say, -3. Then the matrix used to represent this is given by what's in the box here. Now, all you have to do is you'll be given the value for A, you'll be given the value for B, is to form the matrix for this particular application. So, in our case here, T, the A value is 4, the B value is -3. So the matrix is going to look like this. So it's 1, 0, 0, 0, 1, 0, and lastly A is 4, B is -3, and the value down here is 1. Likewise, in the exam you'll be given the formula for a rotation matrix. So you'll be just given what's in the box here, this particular piece of information, which tells you how to form the matrix, and you'll be told that it'll be for a rotation. You need to understand what this exactly represents. This matrix here represents, suppose a 2D point is rotated about 0, 0, right, in an anti-clockwise direction by an angle theta, then the matrix used to represent this is given by this. Right, so the important thing is that the rotation is anti-clockwise, it's about 0, 0 by an angle theta. You'll be given theta and you'll be told the direction and about what point you want to rotate the point. So it's up to you then to put the appropriate values in and form the matrix, and we'll be doing that later on in the video. The next matrix is the scaling matrix, and again, if I just put a box around this, you'll be given this in the exam and you'll be told this is scaling, and you need to know this here. It says that suppose a 2D point is scaled by amount S in the x direction and T in the y direction, then the matrix used to represent this is this matrix here. So for instance, if you wanted to make a particular object 4 times larger, then S would be equal to T would be equal to 4, right? So you just put in the values there and you'd form the scaling matrix S, which would be 4, 4, right? And putting in the values, the matrix would look like this. It would be 4, 0, 0, 0, 4, 0, 0, 0, 1. And the last matrix that you'll be provided with is reflection. So again, here you'll be given this matrix here, and you'll be just told that that's for reflection. In this case, it's reflection my, which means it's reflected about the y-axis. So you need this understanding here. It says that suppose a 2D point is reflected about the y-axis, then the matrix used to represent this is given by this. Okay, so if you think about how you would reflect a point in the y-axis, it would be like this. If your point was here and this was your y-axis, to reflect it in about the y-axis, the point would end up over here. You can also reflect about the x-axis, and hopefully you should see fairly clearly, if your point here was x comma y, reflecting it about the y-axis, it would become minus x comma y, hence the minus here in the x position. If you reflect it about the x-axis, it will be x comma minus y. So if I wanted to write down the equivalent for reflection about the x-axis, I would write down the matrix mx is equal to, and I can form this matrix here by a 1, 0, 0, 0, and I'd put a -1 in here, 0, and then 0, 0, 1. Now we're going to look at applying transformations to 2D points. Now, all of our transformation matrices, let me write that down, all of our transformation matrices, and there were 4 of them that I listed in the previous part of the tutorial, all of them are 3 by 3 matrices. They have 3 rows and they have 3 columns. And when I go to apply my transformation to 2D points, I'm going to do this by matrix multiplication. Matrix multiplication. Now, if you recall, matrix multiplication is a very specific operation. So what I'm going to do is I'm going to have my 3 by 3 matrix right here. Okay, so it's going to have 3 rows and it's going to have 3 columns, right? And I'm going to multiply it by my point to end up with a solution which is going to be the image of that point. To multiply two matrices, this number and this number have to be the same. So the 2D point is going to have to be in some way changed into a 3D column vector, right? It's going to only need one column in it. And the answer then is going to come out in the same shape as it went in. It's going to come out as a 3 by 1. So this solution is going to be a 3 by 1. So if I write that down, it'll say that when transforming a 2D point, it should be converted into a 3D column vector. So if we ask ourselves the question, what should 2, 6 be converted to? 2, 6 is a 2D point, 2, 6, and to transform that point using one of my transformation matrices, what should it be written as? Well, it should be written as a 3-dimensional column vector, so it's going to be 3 by 1. The first two entries are going to be the x value and the y value, and the third entry is going to be a 1. And that 1 is placed in there just so that I can do the matrix multiplication. We now have all the maths we need in place to do typical transformation questions. So let's try that. So here's a question. Using the transformation matrix, translate the point 2, 6 by 4 in the x direction and by -3 in the y direction. Now, as I said to you, you'll be given the formula for the translation matrix, and the formula will be given to you as follows, that TAB is equal to, and you'll be given the matrix, and the matrix is 1, 0, 0, 0, 1, 0, and A, B, 1. Now, what you need to know is that A is the translation in the x direction. So A has a value 4. So filling in these values, A is 4. It's going to be 1, 0, 0, 0, 1, 0. A has a value 4 and B has a value -3. B is the translation or the movement in the y direction, and that's going to be a value 1. Now, to do the translation, we're going to use matrix multiplication, and we want to translate, the point 2, 6. Now, as we saw previously, to translate that point, we have to multiply it by this matrix here. And to be able to multiply it, we have to rewrite this 2-dimensional point as a 3-dimensional vector. So 2, 6, 1, it'll be rewritten as. So to do the translation, I take my translation matrix 1, 0, 0, 0, 1, 0, 4, -3, 1, and I multiply it by 2, 6, 1. Now this is a 3 by 3 matrix, and it's multiplied by a 3 by 1 matrix. These two values are similar, and the solution is going to be a 3 by 1 matrix. So my solution is going to look like this. It's going to have 3 rows and 1 column. Now let me do the multiplication for you. To get this first value here, it's in the first row, first column. So what you do is you take the first row of the first matrix and you multiply it by the corresponding entries of the first column of the second matrix. So what we'll have is that 1 multiplied by 2 is 2, 0 multiplied by 6 is 0, and 4 multiplied by 1 is 4. So 2 plus 4 has a value 6. The next entry, this entry here, it's in the second row, first column. So what I do is I take the second column of the first matrix and I multiply it by the corresponding entries of the first column of the second matrix. So it's going to be 0 multiplied by 2, which is 0, 1 multiplied by 6, which is 6, and minus 3 multiplied by 1, which is minus 3. So what I have is 6 minus 3, which turns out to be 3. And now for the last entry, this entry here is in the third row, first column. So I multiply the third row by the first column. So it's 0 by 2, 0 by 6, and 1 by 1. So this has a value 1. Now this will always be a value 1 when you do the multiplication. So the solution to my problem, right, is that if I started off with a point 2, 6, and I translated by 4 in the x direction and minus 3 in the y direction, well then I end up at a point 6, 3. So 6, 3 is my image or my solution. Now let me move this up for you a little bit and let me show you what this would look like on the Cartesian plane. So if I draw my Cartesian plane, let me make that line a little bit wider, and draw my y-axis, my x-axis, sorry, and my y-axis. So this is my x-axis and this is my y-axis. Let me put in a scale, 1, 2, 3, 4, 5, 6. So this is 6 and this is 2. And let me put in a scale on the y-axis, 1, 2, 3, 4, 5, 6. Now it's just a sketch. So 1, 2, 3, 4, 5, and that is 6. So plotting the first point is 2, 6. So here it is here. So that's where I started off before I applied the translation. And when I applied the translation, I ended up here on the Cartesian plane, 6, 3. So effectively what I have done is I have taken a point, and the point was 2, 6, here it is here, and I just moved it to a different position on the Cartesian plane to 6, 3. If you're talking about a computer screen, you'd just be indicating a point on a screen, 2, 6, and you'd be moving it to a different position on the screen which has the coordinate 6, 3. Now let's look at another question. It says, using a 3D transformation matrix, rotate the point 2, 6 by 90 degrees anti-clockwise about 0, 0. Now you'll be given the rotation matrix, so if I write that down, the rotation matrix is r theta is equal to, and what you'll be given is the cosine of theta minus the sine of theta, sine theta, cosine theta, 0, 0, 1, and 0, 0 in these positions here. Now you need to know specifically that this is a rotation anti-clockwise about 0, 0. So this matrix is correct for this problem in this form. It's an anti-clockwise rotation about 0, 0. The only thing we have to put in is the number of degrees, and in this case theta is equal to 90 degrees. So if I put in theta equal to 90 degrees, I'm going to get r 90. So it's going to be the cosine of 90 degrees, and if you work that out on your calculator, you find that that has a value 0. If you work out the sine of 90 degrees, you have that as a value 1, but it's a minus sine of 90 degrees, and this value is 0. Sine of 90 is a 1, cosine of 90, 0, and 0, and then the last row is 0, 0, 1. So there's my matrix that's going to perform the rotation for me. To do the rotation, what I do is I take my matrix 0, 1, 0, minus 1, 0, 0, 0, 0, 1, and I multiply it by the 2D point which should be written as a 3D column vector. So it's 2, 6, 1. So I perform this multiplication, and what I'll get is a 3 by 1 matrix, so there'll be 3 rows and 1 column. Just as before, to perform this matrix, to get this value here, it's in the first row, first column. So you take the first row of the first matrix and you multiply it by the corresponding entries of the first column of the second matrix. So it'll be 0 by 2 is 0, minus 1 by 6 is minus 6, 0 by 1 is 0. So the first value will be minus 6. Continuing on, the next value will be you take the second row and multiply it by the first column. So it's 1 by 2, 0 by 6, 0 by 1, so it has a value 2, and this value will always be a 1. So if I write out my solution, the solution to this problem is that if I had started off at the point 2, 6, and I rotated it by 90 degrees anti-clockwise about 0, 0, I ended up with the point at the point minus 6, 2. So this is my solution. Again, if I just move this down here a little bit, I can show you this clearly on the Cartesian plane. So again, I'll do the best I can just to do a sketch of it. I'll try to be neat. So there's my x and there's my y axis. So this is x and this is y. And let me set up a scale, 1, 2, there's 2 on the x, and I want to go down to 1, 2, 3, 4, 5, 6, there's minus 6 on the y scale. So on the x scale, sorry, on the y scale then I want 6, so 1, 2, 3, 4, 5, 6. So there's my value 2, and there's my value 6. So I put in my points. My first point is 2, 6. So that's where I started off, 2, 6. And I ended up at minus 6, 2. So there's minus 6, 2 there. Minus 6, 2. Now remember what I did was, if I change colours, I rotated it about 0, 0. Here's 0, 0. That's the origin of the Cartesian plane. So if I just draw a line going to here to indicate like an arm coming from 0, 0. What I did was I swung it around anti-clockwise. So there's my anti-clockwise direction. Anti-clockwise direction. And I swung it around and I ended up here. Right? I ended up here. Right? And I swung it around by a 90-degree angle. You can see there's my 90 degrees. Theta was equal to 90 degrees. So that's exactly as the movement suggested. Now let's look at this question. It says using a 3D transformation matrix, firstly, so there's going to be 2 parts to it. Firstly, translate the point 2, 6 by 4 in the x direction and minus 3 in the y direction, and then, after that, rotate it anti-clockwise by 90 degrees about 0, 0. In the last 2 questions, we have formed the matrices for these 2 transformations. Firstly, for the translation, we had the translation matrix. So for the translation, T I'll just call it. So T, the translation matrix, looked like this. So it was 1, 0, 0, 0, 1, 0, and it had the values 4 and minus 3 here, and a 1 here. For the rotation, we had the matrix, I'll call it R just, R. And if you recall, it was a rotation by 90 degrees, and the cosine of 90 was 0, the sine of 90 was 1, but that was minus sine of 90, so that's 0. And then that was a 1, a 0, 0, and a 0, 0, 1. Now, what we're asked to do is to apply both of these transformations in a given order to the point 2, 6. So let me firstly write the point 2, 6 as a 3-dimensional vector. So it's going to be 2, 6, and I'm going to put in a 1 here. Now, I'm asked to firstly, so remember this is very important because if you remember, the multiplication of matrices is not commutative. So the order in which you write them down becomes very important. So I'm asked to firstly translate the point. So this is my translation matrix here, T. So I'm going to apply that firstly to the matrix. So it's 1, 0, 0, 0, 1, 0, and then 4, minus 3, 1. Then what I'm asked to do is to rotate it anti-clockwise by 90 degrees. So I'm asked to apply the OR transformation to it secondly. So I'm going to write that down. 0, 1, 0, minus 1, 0, 0, 0, 0, 1. Let me move down the page here to give myself a little bit more room to finish the question. The best way to proceed with this problem is to multiply these two matrices here together first. The reason for this is that usually I wouldn't be just applying the transformation to one point as I am here. I would usually be applying it to a whole series of points. And so it will make my number of multiplications less and my overall efficiency greater if I find one overall matrix, which we're actually going to call the combo matrix. So let me do the multiplication. Here I have a 3 by 3 and it's multiplied by a 3 by 3 matrix. So these two figures are the same, so I can multiply, and the result is a 3 by 3. So let me fill out the structure of a 3 by 3 matrix for you. So it has 3 rows and it has 3 columns. Okay, and I have to fill all them out. And then eventually I'm going to multiply it by 261. Okay, so this is here in the first row, first row, first column. So I multiply the first row of the first matrix by the corresponding entries of the first column of the second matrix. So you'll see that it's 0 by 1, which is 0, minus 1 by 0, which is 0, and 0 by 0, which is 0. So that has a 0 value. You continue on and you multiply the first row now by the second column of the second matrix. So 0 by 0, but it's minus 1 by 1, which is minus 1, and 0 by 0 is 0. So this will turn out to be minus 1. Then I multiply the first row by the third column. So it'll be 0 by 4, which is 0, minus 1 by minus 3, which is plus 3, and 0 by 1, which is 0. So this will be a plus 3 value. Keep going and now move on to the second column, or the second row, sorry. First column. So 1 by 1 is 1, and the other two values are 0. Second row, second column, 1 by 0, 0 by 1, and 0 by 0. So again, that's 0 again. And again, the second row, third column, 1 by 4 is 4, 0 by minus 3, and 0 by 1. So this turns out to be a value 4. Move on now to the third row and multiply it by the first column, and you're just going to get 0, 0, 1. This will always be 0, 0, 1, so you can just fill that out without calculating it if you want to. So this equals this, and now all I have to do is this last multiplication. This is a 3 by 3 multiplied by a 3 by 1. Okay. Now before I do the multiplication, let me identify this matrix here as being, what we call it, is the combo matrix. It represents a combination of transformations. In this case, it represented two particular transformations, a translation and a rotation together, and it will implement both of them on 1 or 2 or 3 or as many points as you like. Okay, let me give myself another little bit of space here to do the multiplication. So 3 by 3 multiplied by 3 by 1. These two figures are the same, so you can multiply them, and the answer is a 3 by 1. So let me write it down here. So it's a 3 by 1. Okay, so 3 rows, 1 column. So to get the first entry, what I do is I take the first row of the first matrix, so they'll be highlighted here, and I multiply it by the first column of the second matrix. So it's going to be 0 by 2 plus minus 1 by 6 is minus 1 plus 3 by 1, which is 3. So minus 6 plus 3 is minus 3. So it has a value minus 3. The next one is 1 by 2, which is 2. 0 by 6 is 0. And 4 by 1 is 4. So 2 plus 4 has a value 6. And this turns out to be a 1. So the solution, let me just write it out here, right, is that I started off at my point, with my point 2, 6, and I did two things. I translated it in a certain way as defined by the problem, then I rotated it in a certain way as defined by the problem, and where I ended up is at a new point, and the new point is minus 3, 6. So minus 3, 6 is the solution to my problem. Now let's look at this question. Here you're given a triangle Q, and it's defined by the points A, B and C, and you're given the coordinates there for A, B and C. And the question asks you, using a 3D combo matrix, so a 3D, three-dimensional combo matrix, apply the transformation to Q, which firstly translates Q by 4 in the x direction and minus 3 in the y direction, and then rotates it anticlockwise by 90 degrees about 0, 0. Now this is the same question that we were asked in the previous question that I did for you. So we've actually already found the combo matrix in the last question. So I'm going to write down the combo matrix here. So the combo matrix is this matrix here. So just from the last part, it's 0, 1, 0, minus 1, 0, 0, and then lastly 3, 4, and 1. So the question asks me to apply the transformation to Q. Right? It asks me to apply the transformation to Q. And Q is the triangle defined by A, B, and C. So in essence, all I have to do is I have to take my combo matrix and apply it to A, B, and C, and find the new image points for A, B, and C. So here I go. I've already the first one done because that's the point that I applied it to in the last question. And what I did was I took that and I multiplied it by 2, 6, 1. And where I ended up was minus 3, 6, 1. So the point 2, 6 ended up at minus 3, 6. So if this was my A point, this would be my A dash point, or my image of A under this transformation here. If I move up the page and do exactly the same now for the next 2 points, what I get is this matrix here, 0, 1, 0, minus 1, 0, 0, 3, 4, 1, multiplied by, now the B point. The B point is 2, 10, 1. And that's equal to, now if I do the multiplication, 0 by 2 is 0, minus 1 by 10 is minus 10, plus 3 is minus 7. 1 by 2 is 2, 0 by 10 is 0, 4 by 1 is 4, 2 plus 4 is 6, and this is a 1. So my B point, which is 2, 10, ends up as being minus 7, 6 once the transformation is applied to it. So this is my B point and this is my B dash point. Now applying the transformation to the last point, 0, 1, 0, minus 1, 0, 0, 3, 4, 1. Applying that now to this point here, which is 6, 8, 1. What I get, again, doing the matrix multiplication, 0 by 6 is 0, minus 1 by 8 is minus 8, plus 3 is minus 5. 1 by 6 is 6, 0 by 8 is 0, 4 by 1 is 4, so this turns out to be a 10, and this is a 1. So my point 8, or 6, 8, ends up being minus 5, comma 10. So this is C, this turns out to be C dash. So these 3 points here, A dash, B dash and C dash, form the solution to my problem, because that's where the triangle will end up. Now let's have a look at drawing this to see where the triangle started and where it ended up. So let me move this up here to give myself a little bit of room, and let me draw a Cartesian plane for you. So the Cartesian plane looks like this. There's my y-axis and there's my x-axis. So this is x and this is y. So I'll set up a scale. I'm going to set up a similar scale on both axes, and what I'm going to do is I'm going to go up in twos. So I need to go 2, 4, 6, 2, 4, 6 on this axis, and then upward, or this way here, minus 2, minus 4, minus 6, minus 8. That's minus 8 there, minus 6, minus 4. Do the same on the y-axis. I'm going to go up 2, 4, 6, 8, 10. I'm going to go up to 10. Okay, so let me plot the points. So the first point, the original triangle, was 2, 6. So there's 6 there. So 2, 6 is here. The next point is 2, 10. So 2, 10 is here. And the last point was 6, 8. So this is 8 here. And this is 6. So 6, 8 is here. Okay, now if I draw these, that is my original triangle Q. So this first point was A, the second point was B, and this point here was C. Now let me draw where the triangle ended up. So A dash was minus 3, 6. So let's put that in. Minus 3, 6 is here. So that's minus 3, 6, that's A dash. The next point was minus 7, 6. So minus 7, 6 is here, and that's B dash, minus 7, 6. And the last one was minus 5, 10. So minus 5, 10 is here, minus 5, 10. So that's where my triangle ended up, that's C dash. So if you want to call this Q dash, the image of the original triangle Q once the transformation has been applied. Now let's look at some scaling and reflection transformations. Here's a question. Scale the line joining the points 2, 6 and 6, 8 by 2 in the x direction and 0.5 in the y direction. Now again, you'll be given the formula for the scaling, and the formula for scaling is S is equal to, here you've got S 0, 0, 0, T 0, 0, 0, 1. Now S is the scaling in the x direction and T is the scaling in the y direction. So for our question, the S value has a value of 2 and the T value has a value of 0.5. So our matrix for this particular question is, if I write it out, S is 2, so instead of 2 I put in, or instead of S I put in 2. So 2, 0, 0, 0, T is 0.5, so I put in 0.5, 0, and then 0, 0, 1. Now if I want to scale the points joining these two coordinates, they're 2D, all I have to do is I have to multiply the scaling matrix by my 2 points. So 0, 0.5, 0, 0, 0, 1. So I have to multiply it by a 3D representation of it. So it's 2, 6, 1. And I have to work out the solution. I have to do exactly the same for the next point, 6, 8, 1. And I have to work out the solution. So maybe you could pause the video for a few minutes and try that yourself and see, can you do the multiplication put back in the matrix here, 2, 0, 0, and try that multiplication and see do you get the right answer. So when I do the multiplication, the two solutions turn out to be, this one is 4, 3, 1, and the next one is 2 sixes are 12, so that's 12, 8 by 0.5 is 4, 1. So basically, the 2, 6, let me write that down, 2, 6, now gets moved to 4, 3, and the point 6, 8 gets moved to 12, 4. To see this scaling, we'd have to draw it. So let me move up the page here and draw this on my Cartesian plane. So if I draw my scale, I'll draw it this way. Here's my x-axis and here's my y-axis, and my x scale needs to go up to 12, so I'll go 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12. My y values need to go to 8, 2, 4, 6, 8, so there's my y values, 2, 4, 6 and 8. My first point is 2, 6, so that's it there. My second point is 6, 8, so 6, 8 is here. So that was my original line. And if I change colours and draw in where I ended up at 4, 3. So 4, 3 is here, and 12, 4. 12, 4 is here. So there's my new line. Okay, now you can see that the new line, the old line, the distance between the 2 points here in the old line was 2 to 4 along the x-axis, which is 2, and on the new line the distance along the x-axis is 4 to 12, which is 8. So it got 4 times bigger, and that's what you were asked. Along the y, you can see the distance here was just 2 to begin with, and then it got smaller by a half. It's now only 1 in the image. One of the problems with the scaling matrix is that it has actually moved the line from its original position. This problem can be overcome by using the scaling in conjunction with translation matrices. Okay, we'll try one more problem. Here you're asked, using a 3D transformation matrix, reflect the point 2, 6 in the x-axis. So I'm going to give you the matrix to do that. I'll write it down here. So it's mx and it's equal to, so writing down that matrix, it's 1, 0, 0, 0, minus 1, 0, 0, 0, 1. Now I've given you the matrix, so what I want you to do is to pause the video and just try this question yourself. And when you're finished, turn the video back on and I'll go through the solution with you. Okay then, the solution turns out to be a multiplication of this matrix here, the reflection matrix, minus 1, 0, 0, 0, 1, with the point you want to reflect written as a 3D vector. So 2, 6, 1. Now you just do the multiplication, and what you'll discover is it's 1 by 2, which is 2, and the other two values are 0. 0 by 2 minus 1 by 6 is minus 6, and this turns out to be a 1. So the solution is that 2, 6, it started off as 2, 6, and once you reflect it, the answer is 2, minus 6. So that's the solution there. If you want to draw that and see what it looks like this. So 1, 2, there's the 2, and 6, 2, 4, 6, 2, 4, 6. So that's plus 6, and that's minus 6 here. So it started off at 2, 6 here, 2, 6. This is my x-axis. It's got reflected through the x-axis, so it ends up down here at 2, minus 6.